This video will be dealing with the rationalization of denominators that contain an I. Now, I'm not talking about a physical I from the body, obviously. We're referring to, instead, the imaginary unit I, which stands for the square root of -1. If a denominator has only an I in it, say for instance 5 over I, it's a simple matter of multiplying it by I over I. The reason we do this is I times I in the denominator is going to give us I squared. And as we know, I squared, the square root of -1 squared, is going to be -1. So we're going to be turning an irrational I into a rational -1. That's called rationalizing the denominator. So we multiply the denominator by I so that we can turn the irrational I into a rational -1. The reason we multiply the numerator by I as well is because whatever you do to the bottom, you do to the top. You may remember hearing this quite often when dealing with fractions. Whatever you do to the bottom, you do to the top. So if you want a quick word to help you remember that, like PEMDAS for please excuse my dear Aunt Sally, the order of operations. The word here would be wit. Okay, that's whatever you do to the bottom, you do to the top. Okay, so you can remember that. Whatever you do to the bottom, you do to the top. And when we do that to the top, we get 5i. And so 5i over -1 would then simplify, obviously, to -5i. Simple enough. There can be, of course, be a little bit more to that. Let's say you have 6 over 5i. This is done exactly the same way. We don't care that there's a 5 there. The 5 is already rational. The only irrational part of that denominator is the I. So again, we multiply by I over I so that we can rationalize the denominator. And then the reason we do it to the numerator is so we get 6i up there. And then the negative I squared is going to be a -5 in the denominator and a 6i in the numerator. Now, personally, I like to have that negative up in the numerator, and we can move that freely. There's nothing wrong with that. Okay? So the I, if it's just an I, we just multiply by an I to rationalize. And it doesn't really matter what's going on in the numerator. You could have something along the lines of 7 minus 2i going on in the numerator over, say, 3i in the denominator. All we care about is rationalizing the denominator. We're not trying to do anything to the numerator. The numerator is really just kind of tagging along for the ride. Okay, so we multiply I over I, and that's going to give us a 3i squared in the denominator. Numerator needs to be distributed. So we'll get 7i minus 2i squared. I squareds are -1s, so this is a -1, and this is a -1. So that's going to give us a 7i plus 2 over a -3. And then, again, like I said, I like to put the negatives in the numerator, and we should always put things in the order of a plus or minus bi. The real part before the imaginary part. So it started with the 7 was real and the 2i was the imaginary part, but now the 7i is the imaginary part and the 2 is the real. So we get 2 plus 7i over -3, or if you're like me and you like the negative in the numerator, then that just makes it negative 2 minus 7I over 3. Both of those are perfectly valid. That's it if there's just the I in the denominator. And some people refer to that as a conjugate. They're looking at this as something along the lines of 3 times the quantity of I plus 0, and then they're doing the conjugate of I minus 0, which doesn't do anything, but then they get to have one rule that works all the time. You always multiply by the conjugate, and conjugates always make real numbers. And that's fine if they want to have that rule. I think it's just as easy to just say multiply by I. If there's only an I, you multiply by I. This is a monomial, so we multiply by a monomial, right? I think it's just as easy to say that. The conjugate that they're referring to is when there's a binomial in the denominator. So this would be a situation that they're referring to when they talk about needing a conjugate. There's a binomial in the denominator, 2 terms that include an I. And so then we can't simply multiply by an I, because if we just multiply by the I, then that's going to have to get distributed. So it'll rationalize this term, but then this term will become irrational. So that's not going to help us. All we're going to be doing is trading terms back and forth. What we need to do instead is multiply by the conjugate. And a conjugate is simply the same binomial with the opposite function. All right, same terms, opposite function, like so. Okay. Remember, whatever you do to the bottom, you do to the top. Right? Same rule applies here. So what that's going to do, if we FOIL out the denominator here, we do first, that's 2 times 2 gives us 4. Outer is 2 times the 3i gives us a 6i. Inner is going to be negative 3i times 2, so that's negative 6i. And last would be negative 3i times positive 3i, that would be negative 9i squared. The middle terms will always cancel out because of those opposite signs, the plus and the minus there. That's always going to leave you with the 4, the square of the first term, minus the square of the second term. Does that sound familiar? A difference of squares? It's always going to create a difference of squares. Anytime you multiply by a conjugate, you always create a difference of squares. So that's going to be the 4 minus 9i squared. So if you're comfortable with it, you can just go straight to that. If I know I'm going to be multiplying by a conjugate and I'm going to get a difference of squares, I can go straight there. If you're not comfortable with that, then continue FOILing it out. There's absolutely nothing wrong with that. Remember, in the numerator, that's going to have to get distributed, so that gives us the 12 plus 18i. And we're almost done. Because the I squared is here, we need to simplify this. Remember, I squared is negative 1, so that becomes 12 plus 18i over 4 plus 9 now, because the negative and negative make a positive. 4 plus 9 would be 13. So that's multiplying by a conjugate. If there's a monomial, we just multiply by I. A monomial gets fixed with a monomial. A binomial, as in this case, gets fixed with a binomial, the conjugate. Otherwise, all the rules apply. Whatever you do to the bottom, you do to the top. Distribute when necessary, so on and so forth. I squareds become negative 1s. All of that stays the same. A little bit more interesting would be something along the lines of, let's say you have 5 minus 2i over 4 plus, well, let's just say I. Okay. Again, we don't care about what's going on in the numerator. All we care about is the denominator. We want to rationalize that denominator. The numerator is just going to follow along for the ride. So we do the conjugate of 4 plus I, and we get 4 minus I. And whatever we do to the bottom, we do to the top. Okay. So that's, now we're going to have to FOIL both, right? We FOIL on the top. That's going to give us a 20 Then we have negative 8i and negative 5i will be negative 13i. And positive 2i squared. Over, and we can go straight to the difference of squares here, 16 minus I squared, because we know that conjugates are going to give us a difference of squares, or you can FOIL that out if you choose. Then we simplify the I squareds. That's going to be a negative 1. So negative and negative are going to be positive. Over here, this will be a negative 1, so now positive and negative will be negative. So I have 20 minus 2 now, giving me 18 minus 13i. And 16 plus 1 will give me a 17. Not a problem. One last thing. When we were doing the factoring of special products, difference of squares like x squared minus 4 factored to be x minus 2 and x plus 2. You may notice that those are conjugates, so when you multiply the conjugates back together, you got the difference of squares. And we've been talking about that so far, dealing with the i's. Let's look at one of those conjugates. Let's turn those into x minus 2i times x plus 2i. When we do this, we're going to get a difference of squares. We already know that, so that's going to be x squared minus 4i squared, because there's i's involved now. And we know that the I squared is negative 1, so we can cancel that out. And negative make a positive. So now instead of x squared minus 4, we have x squared plus 4. And when we were dealing with the special products, we would look at that and say, well, that's a sum of squares. We can't factor a sum of squares. We can only factor a difference of squares. But now that we have the I in our toolbox, we can factor a sum of squares. All it does is put an I on the second term of the factors. So if we had something along the lines of x squared plus 9, then we can know that that's going to factor as an x minus 3i and an x plus 3i. If we multiply that back together, you're going to get the x squared plus 9. If we do 16x squared plus 25, the rules are the same. All we need to do is add an I on the end. So it would be the roots with the same function would be 4x and 5i. And then 4x minus 5i. Everything remains the same. All we need to do is put an I at the end. So a sum of squares factors exactly as a difference of squares, except that we have to put an I with the second terms of each factor. So that's something, that's like a freebie, because that's not even in the book. So there you go. That's it. That's dealing with the I. We've already done pulling the I out, simplifying it down, multiplying it, adding it, subtracting it, dividing it, all that kind of stuff. So now all we had to do was rationalize a denominator that contained an I, and we're good to go.